All right, I hope you are ready for more properties of the integral. These are things that, for the most part, we're not going to use today very much, but these are things that are going to be useful as we move forward and we're evaluating integrals. And we're going to get to a point where we're using a lot of these properties without really even thinking about them. They're going to be things that are secondhand to us, like when you're solving an equation, you know you can add and subtract the same quantities from both sides, or you can multiply or divide both sides of an equation by the same number. They're rules that you're so used to that you don't even really think about them. And some of these properties are going to be like that. So the first one is actually a little different. The first one is something that we can really look at right now. And then the other ones we are going to apply in the future. But this first one is really neat. It tells us how to take the integral of a constant dx. Now remember that the integral is the area underneath the curve, and a constant function is a horizontal line. So let's take a look at what this looks like. So here we have our constant function, c, and we're looking between a and b. We're looking at that interval. And if you look at the region underneath that, that region happens to be a rectangle. And we know that the area of a rectangle is the base times the height. The base of that rectangle is going to end up being b minus a, because it's the difference of those endpoints. That's how you find that distance. And then the height is that constant c. And so in the end, the area, which is base times height, is going to be c times b minus a. And that is exactly the value we have for that integral. So if we ever have a constant function on an interval, when we integrate it, we get that constant times the difference in the limits of integration, because it's a rectangle. It's pretty easy. All right, let's take a look at numbers 2 and 3. They're very similar. Number 2 says that if we are integrating the sum of two functions, we can split that up and write it as the sum of the two integrals of those two functions. Basically, we can integrate these two functions separately and add the results together. And the same is true if it's a difference of two functions. You can integrate those functions separately and then take the difference of those integrals. This is going to become useful when we are integrating polynomial functions, because we know polynomial functions sometimes have several terms. And if we are integrating a polynomial that's got sums and differences of terms, these rules tell us that we can integrate each term on its own and then add those up together. That's very, very useful. The fourth one is similarly useful. It says that if we are integrating a constant times a function, we can pull that constant out front of the integral and just integrate the function and then multiply by that constant. This also comes into play when we are integrating polynomials because of the coefficients. Specifically, if we were going to integrate, let's say from 1 to 3, the function 5x cubed minus 2x squared plus 4 dx, these sum and difference rules allow us to split this up into the sum and difference of integrals. So we can write this as the integral from 1 to 3 of 5x cubed dx, and then minus the integral from 1 to 3 of 2x squared dx, and then plus the integral from 1 to 3 of 4 dx. We can integrate each of the terms separately, which is probably going to be easier. And then if we have these coefficients, we can pull them outside of the integral to make the inside even simpler. We could write this as 5 times the integral from 1 to 3 of x cubed dx minus 2 times the integral from 1 to 3 of x squared dx. And then plus, we actually know how to evaluate this integral because it's a constant. Remember, when we do this, we take the constant times the difference of the limits. The constant is 4, and the difference of the limits, 3 minus 1 is 2, and 4 times 2 is 8. So we end up having 8 as that integral. And then once we have rules to integrate power functions, we're good to go right there. So this ends up being very useful. In the end, you don't actually think about these properties every time, because when you do them over and over again, you just go through and you deal with them one term at a time. But these rules are what allow us to do that. We've got one more property of integrals that we're going to look at, and all of these integrals are integrating f of x dx. But the thing that's changing are the limits of integration. And let's actually draw a quick little graph. And we're going to look at some function on an interval. So let's say this is from a to b. And we have a third number c. And I'm going to draw the picture so that it's in between a and b. It doesn't have to be, but this is the example that's easiest to explain why this is the case. If we draw our drawing like this, and this is y equals f of x, some function, and we look at this property, it says that if we integrate from a to c, well, that's going to give us the area underneath that curve between a and c. So if we integrate from a to c, and then after that, we integrate from c to b, that is the area under the curve from c to b. And if we add those two together, the first integral plus the second integral, that's going to be the first area plus the second area, that gives us the integral from a to b of f of x, which is the total area under this region, which looks obvious in this case, right? If we take this first integral, which is this area, plus the second integral, which is this area, we should get the total area, which is the whole integral from a to b. And that is exactly what this property says. There are situations where c is not between a and b. C could be somewhere all the way over here. And in that case, you end up with slightly different drawing, especially because when we integrate from c to b and we're going backwards, remember when we go backwards, that's kind of the opposite of the integral. So there's a little bit more going on. I don't want to get too into it too much because I don't think we need to understand every single one when we've got a beautiful drawing that shows you one of the cases. You can imagine it works when c is not in between a and b. You could even draw it yourself and think about how you would prove that.